Good afternoon to everyone. Today we have the honor and we are very pleased to have with us Professor Mark Girolami. Professor Mark Girolami is the Sir Kirby Lane Professor of Civil Engineering within the Department of Engineering at the University of Cambridge, where he also holds the Royal Academy of Engineering Research Chair in data-centric engineering. Prior to joining the University of Cambridge, Professor Girolami held the Chair of Statistics in the Department of Mathematics at Imperial College, London. He is the Chief Scientist of the Alan Turing Institute, which is the UK National Institute for Data Science and Artificial Intelligence. Professor Mark Girolami is an elected fellow of the Royal Academy of Engineering and the Royal Society of Edinburgh. He was an Engineering and Physical Sciences Research Council grantee for several times within as an Advanced Research Fellow, as an Established Career Research Fellow. He was the recipient of the Royal Society Wellcome Research Merit Award, and in 2023, he was awarded the Guy Medal in Silver by the Royal Statistical Society. The Guy Medal is the most prestigious award awarded by the Royal Statistical Society. He delivered the IMS Medallion Lecture at the Joint Statistical Meeting in 2017 and the Bernoulli Society Forum Lecture at the European Meeting of Statisticians in 2017. Mark, the floor is all yours.
Well, thank you, Laura, and thank you for coming to this talk. I was asked to try and make the talk accessible to numerical analysts, to statisticians, to computer scientists. And so that's what I tried to do, hoping not to offend too many people, but will probably achieve the result of pleasing nobody. But, this is work that's been going on for some time, and certainly some of the phrases in here will be familiar to all of you. What I want to do is very, very briefly remind you of the finite element method, and then the reason why I would argue that a statistical or a probabilistic, or indeed a measure theoretic construction of the finite element method is actually warranted. And by doing so, it means that the combination of data that has been measured and observed from physical reality can then be synthesized and combined in a coherent manner with the finite element model. And what I'll do is I'll give a couple of examples. One example is a very large rail bridge in the UK where we developed this method and used it to, again, model the structure's performance whilst also assimilating data from sensors that were embedded in that bridge. And I'll then very briefly go on to describe how we can take this statistical construction of the FEM and extend it to the time-dependent case and the non-linear case. And again, I'll give some results with subsurface, modeling subsurface waves with solitons. It's very clear to me that this department needs no introduction to the finite element method and its power. But I'm amazed at the impact that the finite element method has had on the physical, on the natural, on the engineering, and indeed on the biomedical engineering sciences. And you can see some examples here of the solution of fields in electromagnetic phenomena, in structural phenomena, and also in biomechanical methods. So I'm really just trying to illustrate that the finite element method has huge impact in the sciences and engineering more generally. And yet it is a very beautiful numerical method with some very beautiful mathematical analysis in studying its performance and so on. Some of the areas that at the Turing Institute we work on where the finite element method has been used is, for example, at the global scale, modeling the evolution of sea ice on the polar caps of the Earth. And likewise, and I believe that one of my colleagues from Imperial, Colin Cotter, is going to be coming to give the next lecture, and he's going to be talking about finite element methods for weather forecasting. And again, we are working with the Meteorological Office in the UK, developing approaches efficient approaches for weather forecasting. Now, this is the time for most of you to take a nap, but some of you, this might be useful. So let's just remember. And now can I move this? Yeah. Just that one here? Yeah. Good. Okay, so the very classical PDE, the Poisson PDE, where we have this divergence of some diffusion tensor A and the gradient of the unknown field being driven by some forcing on some domain omega. And most mathematicians will recognize that the classical domain is usually either the unit sphere, the unit circle, or the unit square. And anything in the physical world can be represented on a domain that is the unit square. But the key here, of course, is that we have a partial differential equation that has to be satisfied within the domain, and there are conditions that have to be satisfied on the boundary. And the key point here is that analytic solutions are very seldom available to us. And so we have to take approximations which are numerical. And for this very simple example here, the numerical example would be that we would take the domain omega and we would provide a discrete representation of it in the form of some sort of finite number of grids that mesh together to form a covering mesh. And then given that, we can numerically solve for the unknown equation, the unknown field u of x. And that is the very basics of it. In essence, the starting point, certainly if you're an undergrad, I take it you teach this to undergraduates, yeah. So the very starting point would be to say that we select some function space, some Sobolev space, H1 in this little illustrative example here, and we would have a set of functions V within this space that satisfy the boundary conditions of the PDE. And what we do is we then construct what is called the weak form of the PDE, where we basically integrate over the spatial domain the product of this test function, set of test functions V, with the left and right hand side of the PDE, and through some schoolboy and some schoolgirl integration by parts, we end up with the weak form representation of the PDE, which we can write in shorthand form, where we basically have this linear operator acting on the function of the field u and the test function v, which of course is just the integral of the dot product of the gradients of the unknown field and the test function and weighted by the diffusion tensor, and then the inner product of the forcing field and test function. Now, what is really nice about this is that we basically have this very simple linear and bilinear form, which when it comes to developing a numerical procedure that is actually going to be practically feasible, this is actually very important. There are mathematical considerations here as well in terms of the levels of smoothness that would be required of the functions, because we're using the weak form. But the next step is then to move from the full Sobolev space to a subspace, finite dimensional subspace. We'll call it nu H. And that subspace is going to be spanned by a set of basis functions, which are defined at specific points across the domain X, and we would have M of these basis functions. And what that means then is that this bilinear form then is changed into something which is now finite dimensional. And so the approximation of our field U at some point in the domain X, right, is just going to be the weighted combination of the basis functions. So just a classical representation. And what it means then is that we now have a linear system here, right, an m-dimensional linear system, and the choice of the basis functions means that we can actually define a linear system which, for computational purposes and numerical purposes, can actually be very attractive in terms of how the space is actually covered, and in terms of how the computation would follow on. So, of course, the geometries of the domain that we are interested in reality are not the unit square, despite the number of oil fields that I have seen modelled as unit squares. Some very complex geometries. You saw the biomedical example with the jawbone, the structural engineering one with very, very complex and determinate structural example. So, you know, we can now cover very complex geometries for the domain. Something that's very important is that this finite dimensional approximation UH, there are results in terms of the consistency of the approximation error. So we can see the L2 error here between the infinite dimensional function value and its finite dimensional approximation, right, is bounded by, okay, so we have the smoothness of the underlying function, but in essence, it's dominated by h squared, where h, of course, is basically the sort of characteristic dimension of the mesh that is used. So this is very important, because we now have theoretical results that tell us about the rates of convergence, and therefore, you know, the bounding on the error that our approximation will have, and these theoretical results have very, very practical important implications when designing software and also modeling some phenomenon. What we end up with at the end of the day is that the finite dimensional representation just defines a classical linear system. So the matrix, the m by m dimensional matrix A, will have elements that are just the bilinear form acting on the ith and the jith basis functions. U is just going to be the vector of all of the basis function weighting coefficients. And B, of course, is just going to be the inner product of the forcing and the basis function. So we've got a deterministic system of equations, and we can solve that using many different methods. So it's a very powerful framework to turn description of some phenomena via PDEs into either a linear or a non-linear deterministic system of equations. And there has been decades of work developing numerical linear algebraic schemes and so associated software codes and algorithms to solve this particular system, so multi-grid methods and so on. So this is great, and this gets us to where we are now. It's business as usual in solving these incredibly complex problems with multiple physics, potentially physics, chemistry interacting, and so on. Fantastic, a real triumph. However, believe it or not, our mathematical models are not always exactly correct, in the sense that they are mathematical idealizations of physical or chemical, whatever process that is based on various assumptions. And so we therefore have an inherent uncertainty due to this mis-specification of our mathematical description, our system of PDEs. The diffusion tensor I just described in civil engineering, that could potentially describe material properties, which who knows what they are, especially in something like soil mechanics and so on. So there is no doubt that there is potentially mis-specification. We could have uncertainty associated with our forcing, uncertainty as I just described in our diffusion tensor, uncertainty in the satisfaction of the boundary conditions. Working with climatologists and meteorologists, you realize there's a lot of physics that isn't really understood and is missing in some cases. And indeed, even the geometry of the domain could be uncertain. And now, of course, we have sensor systems at the global scale, whether that is satellites, and we have sensors right down at the micro scale, where we can measure whole fields of pressure or velocity, in very complex geometries that as you might find in like human systems. And they are all producing data. They are producing information about some of the quantities of interest that are of importance to us when we start off with our PDE description, or our system of PDE descriptions of the phenomena that we're wanting to study. And so the question then is, how can we use this data to best effect, or do we just ignore it? Well, as someone who held the chair of statistics at Imperial College, you'll be unsurprised to know that I would argue that data containing information about a system that we have in an incomplete manner specified and therefore misspecified is actually extremely important and could be extremely valuable in refining our models or doing inference on quantities of interest that are particularly complex. And so the question is, how do we assimilate this data? How do we capture that uncertainty? And the starting point for this work was, well, look, the finite element method is basically based on the fact that we have some well-defined Sobolev space in which the solutions reside. And those Sobolev spaces have got, beautiful geometric properties, properties of the norm or the inner product, which are useful for analysis and for construction of computational algorithms. But if we want to characterize uncertainty and we want to assimilate data into our overall representation, then we need a further mathematical structure in that space. And the argument that we made was that we need to endow that space with the structure which is defined by a measure and a probability measure. Okay, well, that's no problem. We can do that. But wait a minute. Sobolev spaces, infinite dimensional, Lebesgue measure in infinite dimensional spaces, not defined. So we need to think about what is the sort of measure that would act as a reference in this equivalence class function space that would be well defined and would also serve as well when it comes to both analysis and then development of actual algorithms to implement these methods. Now, we could have a whole series of lectures, and maybe in your third or fourth year, there are a whole series of lectures on how do you define probability measures in Hilbert spaces, Sobolev spaces. You're going to have to trust me that a measure which is well defined in such Sobolev spaces is the Gaussian measure. Okay, so we have Gaussian measure over the equivalence class of functions U, which satisfy our PDE. And this Gaussian is a classical Gaussian measure in the Sobolev space, which is defined by some function, which is a mean, and some covariance structure, again, which is well defined in the infinite dimensional space. So it would be trace class, it would be atomic class, and so on. I'm not going to go into the details because we don't have time. But if we then endow our space with this Gaussian measure, then it means that we can now use classical tools to change that measure or to define radon-Nikodym derivatives, such as, so here's an example here. This is our reference measure in the space. If we observe some data, let's call it y, right? We could then define the measure, right, which is conditioned on y, right, with respect to this measure here. And of course, because the Gaussian measure is well defined in these Hilbert spaces, these Sobolev spaces, then this change of measure is also well defined. And so we could do things such as, well, we can now start to think about doing statistical inference. And so the conditional measure, right, is now going to be absolutely continuous with respect to the reference measure, provided, of course, that this energy function here is well defined in the appropriate space. But again, these are more technical details. So this is at a very abstract level. We have now got a space with a reference measure, and we can then change that measure if we are conditioning on observed data. So that gives us a way now of assimilating data. The question then is, well, this is on the space, but how do we now construct an FEM method which exploits the fact that we have a reference? So we need to now define the reference measure. So the simplest approach, and this is really just for pedagogical reasons, let's take the weak form as we just defined it, and let's say that we have uncertainty in our forcing function, right? So the forcing function has some uncertainty which is represented by, again, some Gaussian measure. I'm just assuming for the purposes of this presentation that the mean function is 0 and there's some covariance function associated with the covariance operator of the measure. Okay, that's all fine. Now, if we then take a spectral expansion of the field U of X, and we represent that in this form here, then what should be fairly straightforward to see is that the push forward of the measure on F to a measure on U, because this is all linear, then we induce a subsequent Gaussian measure on the coefficients U. So we can then project down onto our finite dimensional space, which is going to be just a standard truncation of the spectral expansion. And what we end up with in the finite dimensional case is a Gaussian law on the finite number of coefficients of our FEM method. And if you just turn the handle on the algebra, so we would say that we have the vector of FEM coefficients, which are going to be conditioned on whatever the functional form of the forcing is, and whatever the parameters, in this case here, of the diffusion tensor, plus whatever parameters there are in the actual Gaussian measure on the forcing. And that conditional is then going to be Gaussian. It will have a mean function, which is just the Gagliorcan solution. And the covariance structure, well, we have basically the mass matrices acting on this matrix G, which is basically capturing the covariance structure that is propagated from the Gaussian on F, acting on the various basis functions. Now, what this means from a practical perspective, if this is the standard Gagliorcan solution, then there's lots of software codes, lots of commercial software codes that will give us this. This requires a bit of work, but again, from an algorithmic perspective, especially if G has certain sparsity structures, can be solved fairly straightforwardly as well. But what we now have is a probability distribution over our PDE FEM coefficients, which captures the uncertainty, in this case, related to the forcing function. And this, of course, is now, from a statistical perspective, a probability, a finite dimensional probability distribution on which, a conditional one, on which we can now, well, we can now start to exploit the various tools of statistical inference. Of course, we need to consider the choice of basis function, and that is, an ongoing work in FEM. But in essence, what we now have is this starting point for the construction of a statistical finite element method. I think what's probably important to say here, and I'll just repeat it again, is that this is the standard numerical solution. But we now also have this covariance structure associated with uncertainty, which we represented in this form here. Okay, well, that all sounds good. A little bit of analysis first. The classical FEM analysis relies upon arguments of approximations of functions in Hilbert space. But now what we are doing is we are relying on a probability measure, the structure that we now inherit by defining a probability measure on the Sobolev space. And so the question then is, how does the convergence, how does the rate of convergence, is there consistency when we are now thinking about convergence of probability measures on these functions as opposed to the actual functions themselves? And how do they relate to the standard, the classical results? So we published a paper just on the analysis of this construction here in SciAm UQ. And if I just cut to the chase, one of the key things here is that we're looking to assess, do the randomized realizations U of H, do they tend in some sense to the actual function U as the as H tends to 0? So one of the issues that we have here is that we don't have any guarantees that the measure in the full Sobolev space will be continuous with the measure in the finite dimensional space. They may well be mutually singular. And so that means that the sort of standard analysis that would take place by using some sort of divergence, Kullback-Leibler or Fisher or Hellinger distances, we can't really use those. So the approach that we took is we took the Wasserstein 2 distance as the distance that we would use in terms of trying to characterize the convergence, the rate of convergence of these measures as H would tend to 0. And I mean, cutting a long story short, if you have trouble sleeping at night, I would certainly advise you to get a copy of the paper and follow through the analysis. But you know, not looking at technical details, but the Wasserstein 2 distance between the probability measures on the space H1 and the probability measures on mu H, right, is bounded by H squared. And this is really very comforting to know that the measures that we now think are of importance, right, we haven't broken anything in terms of the efficiency of these estimators or of these approximations. We get the same rates of convergence as we would in the fully deterministic case. And of course, you can see that, you know, as h tends to 0, then you know, basically the measure will collapse onto a Dirac measure on f, and then on the application of the Green's function, so the solution basically. And again, we can see that the L2 error would, of course, converge at order h squared, and the Wasserstein 2 distance on these Diracs would, of course, just correspond to the classical results. So this was very comforting. It meant that letting statisticians loose in numerical analysis methods, we haven't broken anything, which is good. Right. Okay, so we've constructed this reference measure. We've now got a probabilistic construction of FEM, and we could use the whole statistical toolbox given this. The one example I'll give you is, let's say that we get data, right? We've got n, or we make measurements. If you think of our unit square plate, imagine that we've got n little sensors and we've made some observations and characterized by the vector y. If we had full knowledge of the true process, then the measurement process, you know, would describe everything that we need. But because I argue that our FEM is solving possibly quite highly misspecified mathematical representations of the true underlying generating process, then this data could actually be quite useful, and I'll show you just why shortly. So we've got these statistical constructions of our FEM, and the reference measure is, of course, based on the model as well. So we can use either frequentist, Bayesian, or score-based, whatever inferential frameworks would be appropriate, can now all be deployed. So if I just, as an example, take the Bayesian formalism. So let's say that we have a likelihood function, probability of our data y, conditioned on the value of the FEM coefficients and whatever other parameters there are in our model, we'll just call them W. Well, from a Bayesian perspective, our reference measure, P of U of H conditioned on F and so on, right? We could interpret that as a prior probability over the values of the function coefficients. Now, we have data y. So the Bayesian formalism would tell us that the prior multiplied by the likelihood would give us a posterior. But look at this. This is the posterior over our coefficients once we've observed data. And so what this is allowing us to do is, in a coherent way, a statistically coherent way, combine whatever prior understanding, prior assumptions, prior knowledge that we have about the system we're modeling, PDEs, and we can combine that with our observed data. And what that allows us to do is update our prior assumptions once we have made observations and correct any mis-specification based on the information about the system that the data Y has. So this is extremely powerful, and this is really very exciting, actually, when we started to look at this. Because it now, from an evidence-based perspective, can now really allow us to start to critique the assumptions in our models and provide evidence in support of the assumptions, or not, as the case may be, of our models. So this statistical FEM and the Bayesian interpretation, prior construction, now allows for information that we know about physics or the chemistry or whatever of the problem to be incorporated in the inference procedure. And I've got some examples here where we can do this in an analytical way. There aren't that many examples where we could do it in an analytical way. We have to resort to stochastic computational methods, such as MCMC and so on. But this is very nice, I would argue, from a blending of mathematical modeling with statistical representation, and ultimately, with data-driven science. This is an example where we have been deploying this methodology. These are bridges that were constructed up in the north of England, in Staffordshire. And when they were being constructed, my predecessor, who held the chair that I currently have, he convinced the construction companies to embed a network of sensors in the actual structure. These were fiber Bragg optical networks that would measure deflection and then ultimately strain across the whole of the bridge structure. So in essence, what we have is a bridge which gives us data. We have a model which represents the bridge, and of course, is suitably misspecified because of the simplifying assumptions that are being made about it. And to ensure that we got research funding, we describe this as a digital twin of that bridge. But in essence, all that we were doing was taking the mathematical model and its numerical solution and combining it through this statistical FEM construction with the data, the real-time data that we were getting from the bridge structure itself. And of course, the bridge structure looked like this. The deformations are elastic, so everything is nice and in the linear regimes. I'll just, oops, wrong button. Right on. I won't go through the technical details. I'll just show you some of the pictures. So these are the mean functions as a train goes over the actual bridge. Right. So these are the stress profiles. This is the data from the bottom of the bridge. This is the top of the bridge, and these are the carriages going over it. And so this is what we did is we had an FEM, statistical FEM solution, which actually now assimilates data every time a train goes over it. So the idea being that we can then update the model. From a commercial perspective, the rail company would like to be able to use this to assess the integrity of the structure, how it's performing structurally and so on, without sending out engineers to visually inspector and so on, but we could do it in a data-driven manner. So this was quite nice. It was a nice solution to a very real problem. What I want to, in the last 5 minutes, some of you will be saying, yeah, but look, that was linear, a linear push forward, everything's straightforward, you know. So what we did is we looked at time-varying nonlinear systems, and in particular, we looked at solitons. We were working with British Petroleum off the west coast of Australia, where they had a number of liquid natural gas stations that were situated off the west coast. And one of the biggest, well, there was a number of concerns, but one of them was these subsurface waves that would build up and would crash into the structures and potentially potentially deliver catastrophic destruction in some of the subsurface structures. And so we wanted to look at how could we actually use soliton models to help these engineers. So this is a classical time-varying, non-linear PDE. I'm sure probably some of you will have studied this class of PDE, these wave style equations. Anyway, we can then just go through the same procedure of defining a reference measure, now obviously in space and time space, and then just turn the crank on defining what the reference measure would be. Probably unsurprisingly, if we had a time-varying linear PDE, then the probability measure is described by a Kalman filter. No surprises to probably some of the Egypt academics in here. But for the nonlinear system, we can just go through the whole process of defining a sequential construction, a filtering measure of the FEM coefficients for this class of model. Again, I won't go into the details, but yeah, we were able to develop fairly standard routines to propagate this uncertainty and to assimilate data into the models and actually assess, you know, in the Proceedings of the National Academy of Sciences paper, we had a number of candidate models based on various assumptions, and then given data from we were able then to rank the models based on, you know, how closely they represented the actual data. And again, a very classical statistical set of tests that can be done and brought to bear on the mathematical modelling that we are undertaking. We did an experimental study where we had a wave tank and we had a number of gauges in the tank. So we were able to actually make measurements, you can see here, at each of these points in the tank. And you can see the data here. You can see how the wave actually builds. So what I'm showing you here is a realization of the solution, the FEM solution, when we just use the reference measure. So we don't take into account the data. And then the blue representation shows you what happens when we update the reference prior based on the data. And of course, there is a mismatch. And what you can see is that the loss of phase is actually brought into line because of the assimilation of the data from the waveguides. So that was, that was quite nice. It enabled us to demonstrate that this construction can be useful for time-varying nonlinear systems as well. Now, let me just close by saying that most of you, unless you've had your head buried in the sand for the last couple of years, would have come up and met generative AI methods. And these generative AI methods are basically using Langevin diffusion style SDEs. Now, it turns out that we can actually use these Langevin diffusions, just the classical SDEs, to actually generate realizations from the measure that captures the FEM solution. And I think this is really beautiful. And Laura's work, physics-informed statistical learning. I would say that, this is one part of that physics-informed statistical learning. I'd actually go further and say it's mechanistic representations because, there's chemistry, capture chemistry and so on. Anyway, the bottom line is that we can use these diffusions to draw samples to simulate FEM solutions that follow the probability law that captures what we know or what we've assumed about physics and our levels of uncertainty. And again, the analysis, well, it shows that it will converge. I mean, it always converges if your step size, well, if the number of steps you take tends to infinity and your step size tends to 0, but that's not particularly useful. But it shows that these sorts of constructions will converge. And if we look at, the actual systems themselves, right? So this is the matrix of the bilinear form. The rate of convergence is going to be gated, of course, by basically the conditioning of the mass matrix, which is well known. But again, this is now represented in a statistical or a stochastic framework. So all very nice. So let me just conclude. I'm arguing that if we just add that additional structure in the Sobolev space of a measure, then we can construct a statistical representation of FEM, and it allows us to synthesize data with our mathematical models. We've developed it for linear and nonlinear, for static, for time-varying systems. And we've got a number of papers, mainly in SIAM journals, SIAM UQ, Proceedings of the National Academy of Sciences, CMANE, some more SIAM, and Journal of Computational Physics, which I haven't included. So I've taken up my 45 minutes, so I'll hand back to your chairperson, Laura.